Welcome guys to this new video. This video is the first of some videos that we're going to take a look at about some common probability distributions. They are so common that they even have a name. The first of these distributions is the binomial distribution. So the context in which this distribution arises is a context of an experiment where we observe a sequence of identical and independent trials. So think about a series of coin tosses, a series of experiments in which we throw a die or any number of dice, where the result of each outcome is independent of each other, and where the experiment is identical in every way in each of these trials. So there are some examples. Think about an assembly line where we hope to have a systematic way of building, let's say, motors. So and each of these motors are going to be independent of each other. So and the building of each motor is going to be identical to each other. But there's a twist. We can only have, let me write this, two possible outcomes. One of these outcomes is going to be called a success, and the other one is going to be called a failure. So we need to be careful, because when we talk about success, we do not necessarily mean something positive. With the next example, I think you can understand what I'm saying. Another example is, how about if we think about a series of dart throws to a bullseye. So one of these outcomes is a success, so we can consider a success if we hit the center, the red center here, and a failure if we hit anywhere else. So what's going to be the success and the failure here in the assembly line example? Well, think about quality control. Either the motor is defective or it's not. So for the binomial distribution, I want you to think about something that we're going to call a binomial experiment. Let me write it. So a binomial experiment is going to have some properties. I'm going to copy this from my notes so I can spare you of my terrible handwriting. So here are the properties of a binomial experiment. So first of all, we're going to have a fixed number of identical trials. So whenever we're talking about the binomial distribution, I need you to think of a fixed number of identical trials. So we know in advance how many trials we're going to make. The second property is that we have two outcomes, success or failure. Remember, success doesn't necessarily mean something positive. We're going to call the probability of success in a single trial P, and the probability of failure is going to be the complement of P, which is 1 minus P, and we're going to call that Q. So we're going to have two probabilities, probability of success P and probability of failure Q. Fourth property, the trials are independent. So again, think about coin tosses or tossing a die. And finally, this fifth property is super important, guys. You should know this by heart. The random variable of interest in a binomial experiment, let's call it y, is going to be the number of successes observed during n trials. What do I mean? Let's say that we have 10 coin tosses. And let's say that our random variable y is going to be the number of, I don't know, tails in 10 coin tosses. So of course y is a random variable and it can take the values from 0 to 10, right? We can have 0 tails or 1 tail all the way to 10. We don't know how many tails we're going to get in 10 coin tosses. That's why y is a random variable. The probability of success in each coin toss is going to be, of course, 1/2. The probability of failure, again, is going to be 1/2. We know that coin tosses are independent. Of course, we know that the trials are going to be identical, and a fixed number. We're going to make 10 coin tosses. Before we know how many we have, we know that we only have 10 chances. So that's a very basic example. So let's see another example where a success is not necessarily something positive. So how about this example? Let me copy it. Here we go. So imagine that we have a detection system with 4 radars, 4 identical radars. Let me paste my radar here. So we have 4 identical radars. They operate independently of each other. Now we're going to have this probability of detecting an intruder, and the random variable of interest is going to be the number of radar units that do not detect the plane. So in this case, we're going to be considering a success as a radar not detecting the plane. So maybe that's something positive for the plane pilot, but not so much for the people who operate this detection system. So here the success is going to be to not detect the aircraft. So is this a binomial experiment? Is this a binomial experiment? Well, let's take a look at the properties of a binomial experiment. Here it is, sorry. Do we have a fixed number of identical trials? Yes, we have 4 radars. Each radar is going to be a trial. Either the radar detects the airplane or not, so we have 2 outcomes, success and failure. The probability of success is going to be P. So in our case, what's going to be the probability of success? Well, the probability of success is going to be 0.05 because the radar detects the plane with 95% or 95% of the time, sorry. But since we are interested in the probability of not detecting the plane, then the probability of success is going to be 0.5. It's going to be the same for all radars. Of course, the probability of failure is going to be 95%. The trials are independent. Yes, here we have it. They work independently of each other. And the random variable is the number of successes in n trials. Here, the number of radars that do not detect the plane. So yes, we have all the properties of a binomial experiment. So sorry, that's a check mark to represent that yes, this is a binomial experiment. So let us define. Let me show you what I just said. We have a fixed number of identical trials. We have probability of success and so on. Let me just copy this and plug it here. So this is the result of our analysis. We have 4 radars, so we have 4 identical trials. A success is going to be the aircraft not detected, a failure that it is detected. The probability of not being detected is 0.05. The trials are independent. So yes, we have a binomial experiment. So let's work. Let me show you the actual definition of the binomial distribution. Let me write it down here. So a random variable, let's call it x, is said to have a binomial distribution based on n trials with success probability p, if and only if every probability can be computed in this way. Of course, since p is a probability, p has to be between 0 and 1. We're going to have a fixed number of trials. This fixed number is going to be n. So here we have a combination, right? I will explain you why we have this coefficient here. So let's work with an example. And of course, this distribution is very important because it has many applications in quality control. We're going to see that. So let me copy the next example. Here it is. So suppose we have 5,000 electrical fuses. 5% of those are defective. So let's say that we take a sample of 5 fuses and we test those 5 fuses, and we want to find the probability of observing at least one defective. Remember that at least one defective means that we can have either one defective, 2 defectives, 3, so on until 5. Why 5? Because we only have 5 fuses in our sample. So here you can notice right away that n is going to be 5. So what's going to be the probability of success? P. Since we're interested in the number of defectives, then P is going to be 0.05, our 5%. Q, of course, is going to be the complement of that, which is just 0.95. And we're done. X is going to be the random variable that represents the number of defectives in a sample of 5. In a sample of size 5. So let's use the definition to compute that probability. So let me write it down here. F of x is going to be this combination: n choose x, p to the x, q to the n minus x. Sorry guys, let me rewrite this ugly x. So now we are left to substitute everything in our definition. So the probability of at least one defective is going to be the probability of one defective plus the probability of 2 defectives, and so on until 5. But we're smarter than this, and we can use something else to compute what we want. We don't want to compute 5 times the same probability. Well, it's not the same, but using the same formula 5 times. So what we can do, the probability of at least one defective is going to be 1 minus the complement of this. What's the complement of that? Well, that's just 0 defectives. So how to compute f of 0? Let me move a little bit up. F of 0 is going to be just here. Let's substitute this combination. So n is going to be 5, of course, and x is going to be 0. P is going to be 0.05 to the x, which is 0, times q to the n minus q, which is 5, n minus x, sorry, 5 minus 0. So of course this is just 5, so let me just write 5. So this example is very easy, so please try to make this computation on your own, and you should get something like 0.774. So the probability of 0 defectives can be plugged here, and this is going to be 0.226. So let's talk about a little bit about this combinatorial coefficient. So in this case, since we're looking for 0 defectives, this coefficient has to be 1, right? 5 choose 0, or n choose 0 is going to be always 1. But let's say that we want to know f of 2. Let me move a little bit up. So let's say that we want to compute f of 2. Then, according to our definition, this is going to be 5(2) times this times this. 5 minus 2 is just 3. So why do we have this? Because the 2 defective fuses out of 5 may be the first 2, or the last 2, or the first and the last, or the second and the third, and we have many ways in which we can have 2 defectives in a sample of size 5. The same thing happens when we talk about f of 1. When we talk about f of 1, we're going to have 5 choose 1. Why? And the rest, right? Because if we have 5 fuses, 1, 2, 3, 4, 5, then either this can be the defective, or this, or this, or this, or this. So we have 5 ways in which we can have 1 defective out of 5, or 2, or 3, or any number that we choose. So that's why we're working with combinations. And remember, it's a combination and not a permutation, because we don't care if it's the first, or the second, or the last. We just care that we have 1 or 2, or whatever number that you want here, number of defectives. So that's why we have that binomial coefficient. So that's it, guys. Very simple. If you are going to leave with something of this video, please let it be this. Please, guys, learn this by heart. The random variable of interest in the binomial distribution is the number of successes in n trials. So thank you, guys. See you next time.